Welcome back. Next section, we will have two speakers with us. The first one is Wang from Texas Instruments. Not a while ago, TO has released a new product. It's a car radar ASIL module. It can be applied to a wide range of applications. Today, we have Jess here to update the module use to different kind of applications. Let's welcome Jessie. Thank you. Hello, everybody. Because of a pandemic, I see everybody is wearing masks. So, for myself, when they told me that it's okay, I don't have to put on my mask, so it will make me easier to talk. In TI, I was in charge of wireless products, and car radars are also within my duty. Today, I'm honored to be here to share with you car radars and its next generation technology development. Let's move on to the next page. I cannot control the... Oh, great, it's working now. For my agenda, it covers two domains. First, we will look at the market demand and the trends, because that will move us to move forward. And the second section, we're going to talk about the radar products we have in TI, including image radar, parking radar, in-cabin radar. For the trends, this shows the SAC standards. For most of us, probably already know this pretty well, because we know there are 5 levels of driving automation. Our dream is to reach level 5. Currently, most of the car makers are saying that they have reached level 2 or level 3 in terms of technology development. And we are talking about the regular vehicles, not like a high-speed train or MRT. For level 2 and 3, their biggest difference is either human being or machine is driving the car. For Tesla, it says they have reached level 2.5. Most of us would think level 2 is kind of not high-end enough, because it's machine assisted and the human beings has to drive still. For most of new car owners, whenever they initiate the adaptive cruise control, and then the driver has no need to control the car. However, if your hands are off the wheel for like 15 seconds, then the car will want the driver to put back the hands, because it's believed we are at a stage that humans still have to drive the car. As we move into higher levels, we will need more automotive technology like sensors, AI technology. Next is from Europe. It's the Euro NCAP. The alliance is set out to develop new cars and establish new standards. It's their roadmap for 2025. As we can see here, you can see several items on the left. all these important features should be included in new cars. For example, AEB, emergency braking, and radar has played an important role in this technology. And next is the driver monitoring system. The machine has to detect if the driver has a fatigue problem. And there have other features like child presence detection to avoid children have been left in the car. So those has set up time frames for the new feature development, and in which radar plays very important role. Next, let's look at the incidents in the US. It's a report saying that throughout 1998 to 2020, there were 849 deaths as a result of child being left in the car. And we are talking about deaths here, not just heat stroke. For most of the causes was brought up because the adults just closed the door and left the car thinking it's not a big deal. Take Taiwan, for example. Our summer is pretty hot. If you just leave the car for 5 minutes, the indoor temperature will go up to pretty high. How can we solve such a problem? Human beings have developed a lot of technology. How can we allow such kind of problem happening? So technology can help. Because of those demands, vehicle radar has been evolved to a new direction. We know vehicle radar used to stand for 24 gigahertz, but this bandwidth is not good enough. Resolution is not good enough either. So it's now moving on to around 77 gigahertz. As we can see on the right-hand side, in the US, Europe, China, Korea, Japan, all around 70 issues. They are all different frequency domain. And these will allow us to have good enough resolution. For US FCC, for Europe there are CE. Those regulations have set up a special domains and they will be preserved for vehicle application. And for on the left-hand side, there are 60 eaches. Those are used for non-vehicle application. In 2019, the in-car can only use 60 gigahertz. And for TI, our radar is one single chip and can be applied for industrial use. And then we cannot use 77 gigahertz. So we move on to 60 gigahertz. So this is ISM band for industrial and medical use. License is not required. For radar development, the international regulations should be taken into consideration. Next, let's look at an example. It's a report from Mercedes. I got it from a magazine. As you can see here, This is a test on the environment around a vehicle. At the beginning, we have ultrasonic sensors. At the parking, for example, 20 meters will be sufficient. But in 2020, because the speed has increased, so the cover range has extended to 80 meters. You can imagine that you will wish your vehicle can detect to the range of 80 meters. For the size, it's also called blind spots for the driver. For blind spot detection, if using ultrasonic sensors, the range is about 1.5 to 4.5 meters. But with the radar technology, we can do as far as 20 meters. But it's not sufficient. The target is to reach 80 meters. 40 meters to 80 meters. As for the front, that's the most critical area for driver because the time braking could occur. At the front, the solution is usually camera, and the requirement is 500 meters. 500 meters. It's very difficult. With radar, at the front, we can, for short range and the mid range and the long range, we have different distances. For mid range, that's about 100 to 150 meters, and for long range, it's about 250 meters. And in the future, the requirement is to reach 500 and to even 800 meters. It's really a challenge. It does make sense, so if you are driving at 100 kilometers an hour and there's a car in front of you, then there are no barriers in between. And if a collision occurred, the speed could be like 200 kilometers per hour. If the detection can reach 500 meters, then the time to respond is still only about 2 to 3 seconds. Therefore, the ideal is to detect further to have better field of view.
So I've explained the demand for you, and in this page, I'm going to explain what solutions can we provide. In the left, you can see that we're offering single chip. We have pure transceiver, and we can include different areas. And we are not using silicon germanium. We're using other materials because the control of the switching time and the stability can be controlled to a very accurate state. So with the new material, we could produce chips with better qualities. And it is also cheaper and goes in line with the safety regulations. In the right-hand side, we have different applications. For example, for mid and long-range imaging radar. In the middle, we have the automatic parking radar and in-cabin applications. which are very hot topics for during these years. First of all, let's take a look at image radar. You can take a look at these pictures. Say, 40 meters in front of this car, there's an obstacle which is 1 meter high. The angle is only 1.4 degrees. So I have to make sure how high this obstacle is. I have to know how the height of the tunnel in case the car is too high for the tunnel. And say in the highway, there's a car in front of you at a distance of 100 meters. And the distance between cars is usually 3 to 4 meters. So you can see the distance of cars in the highway. Say, if there's a car right in front of you, going towards you, that would be very terrifying, because you would want your radar to be able to detect it. If there's an error in the detection, then the result will be disastrous. And if we have a range of 500 meters, then the angle would only be 0.3 or 0.4. That would be a lot more accurate. Do we have anybody who's working in radar for cars? No? Nobody? They wouldn't recognize it. So if anyone has any questions towards these radars, you can come to me later. For example, in our single chip radar, we have 3 antennas. So say the angle is 180 degrees. We would have a 15 degree for the resolution. And so if I want the resolution to be more accurate, we will have to add more antennas. This is image radar, and it's image. So here we have an image from the camera. There are 2 cars at a distance of 112 meters. There are also trees. And in the radar, it would be showed like this. So say there's a 1.7 degree of the angular separation. Then we can see there are 2 cars in the radar, trees, and fence. That's how the radar would recognize these objects. It is even more clearer imaging. If it's a short distance, the radar can even detect the height of the people passing by. Here we have 3 people right here and a bike. So in the short distance, we can detect the difference in height of the objects. For longer distances, we can detect cars. So the field of view for the radar is like this graphic. Right now, we are developing products which can detect 350 meters or more. And for angular resolution smaller than 1 degree, right now only LiDAR can reach that imaging performance. Here, I offered a few links for your reference. And I've mentioned imaging radar. Here we have 4 antennas. So we have 4 times of the power for the antennas.
Next, let's move on to parking and the corner radar. Here, we can use the ultrasonic as a comparison. For the ultrasonic, as you can see in the picture, there are several holes on the bumper. Currently, for 24 gigahertz radar, it can reach to 40 plus meters. And in the future, we expect to develop further to reach 40 plus meter blind spot detection. As for corner radar, we expect to reach 100 meters. What's corner radar? It's rather a new innovation. This one is for car parking. So there are several obstacles in the picture. While backwarding the car, there are lots of obstacles in the space. So we can see here the blue car is trying to park here. For car radar, even though it's towards forward, it's not looking at the front. It's mainly used for corner views. For example, at the cross section, the radar can sense a car coming from the side. So we look forward to reach 100-meter range. In the past, there is no corner radar. Finally, let's look at the in-cabin application, as we mentioned earlier about the child incidents. Next is the driver detection. First of all, it's like the trunk opening detection or door open detection. For in-cabin application, we would like to detect who is in the car, either a dog or a baby. And also we would like to detect driver's condition. And for the future, we would like to detect gesture. How do we do this? For millimeter wave radar, it can detect facility angles and etc. Therefore, it's very good and sensitive at detecting moving objects because it's using FMC technology. So it's good for moving objects. That's what it's good at. If there's a distance and the angle, then I will know it's something moving, or it's moving toward to me or farther down away from me. For moving objects, as the radar is so sensitive, so it can use to detect the heartbeats. My heartbeats can be detected with this technology. With our 77 gigahertz technology, we can reach a very good precision. For baby being left in the car, we would put the radar at the front position around the rear mirror. The baby, we called her Annie. If you go to pharmacy, you can also find Annie. This Annie we actually have different name for the baby. Anyhow, this baby actually has heartbeats and she breathes. So this baby has heartbeats and breathing. And in TI, we have reference design to detect static objects. We would like to recognize it's either adult or baby. So we want to detect its occupancy area. In the vehicle, there are a lot of reflection points. For example, backrest, rooftop, window, footwell, and so on. And those could be interferes. So we have our algorithm to distinguish them. On the right-hand side, you can see the reflection diagram. For all those information data, we need to have sufficient data to recognize what it is. For camera, there are some privacy issues, so camera cannot be a solution. Therefore, we need to have more precise radar technology. For driver vital sign detection, for like a stroke or driver fatigue, in the past we used the camera, but now how do we do it? We use the breathing rate and the heart rate to analyze the driver's situation. Through data analysis, we can figure out how the driver is feeling. And there are lots of positions to put the radar. In this slide, we can see there are different kinds of positions to put the sensors. We are trying to detect the driver's vital signs. Currently, we have several solutions, including FIR, including electrodes, on wheel, on seats, on backrest, and we also can recognize the PPG through fingers. And the radar is one of it. It's a new innovation. Therefore, we put everything together, we can sensor and detect the driver's conditions. This is a very interesting paper. Next is gesture recognition. Radar is good at detecting moving objects, so gesture detection can be completed. In the future, if there is no wheel, then we probably will use gesture to tell the car to turn right or left. For truck opener, it's a new innovation. Those are the applications for in-car use. I don't know if any one of you have questions. We probably have 1 minute. Most of the people don't like to ask questions here, but maybe later, anyone who has questions can come forward to Jessie. Let's thank Jessie for sharing. Next, I would like to connect with my colleague in Germany, Holger. Hello, Holger.
Hello. Thank you for the introduction. Good afternoon and welcome everybody to the second presentation on automotive radar. My name is Holger Gryska. I am located in Munich in Germany, and I worked also many years in the semiconductor business, finally as product manager for radar processing chips. And since 2 years I am with Rohde and Schwarz, and I'm responsible for solutions, combining products for automotive radar. I will guide you through some market trends, tell you about trends and challenges specifically to radar, and also give you a little overview into our solutions. So what is the situation for ADAS globally, but also in Europe and US? Level 2 plus is ready for the mass market. What means level 2? Level 2 means level 3 functionality, but the liability remains fully with the driver. Examples are traffic jam assist or valet parking functions. The maturity of today's sensors like camera and radar is sufficient, but there is still a lack in regulation and standardization for a level 3 homologation and type approval of these advanced functions as level 3. So OEMs, for example in Germany, use this plus functionality to differentiate. Now there is progress on the regulation and type approval side, and there is the first UNECE global regulation in place since January this year. This is a first, I would say, restricted functionality. It's automatic lane keeping without automated lane change. It's a 60 pages document, the regulation addressing all kinds of topics. The maximum speed of the function allowed is up to 60 kilometers per hour. It's only allowed on highway-like roads without pedestrian and bicycle traffic. It's for passenger cars with up to 8 seats plus the driver. Even the minimum range of the sensor is specified. It needs to be 46 meters, which means a minimum driver handover time of 10 seconds. So 46 meters is no challenge for today's sensors, but a handover time of 10 seconds means already some fail operational requirements on the system. Driver monitoring is also required, and activity detection within the last 30 seconds is required. Black box recording is needed, and here the local laws of the countries apply. In addition, for example, in Germany, the data has to be stored for 6 months. And in addition, cybersecurity needs to be ensured. So to get a type approval for a car with this functionality, you have to fulfill many requirements, and a lot of them require new test methods, new procedures which are not existing today in some areas. So it's a challenge all the OEMs are working on currently. If we look even beyond level 3, then there are many challenges still for fast market introduction. The liability is a big challenge. Laws, regulations, and insurances are not yet ready for this kind of functionality. Also on the technology side, there is innovation required. The sensor performance of today's radar and LiDAR, for example, is not yet sufficient at a reasonable price. Also, the software and electrical architecture of a car is completely different from what cars are done today. And this complexity needs to be managed by the OEM in their organization, but also in the supply chain. And new approaches for system validation and certification are required, like I mentioned before. On the financial side, there is a huge investment required, and the time for return of invest is currently hard to predict. The business model is also very important. Cars need to be fail operational. That means you need redundant hardware, and this drives up vehicle cost. In addition to the expensive high-performance sensors. That means the cars will be too expensive for mass market in the beginning, and the OEMs have to look for new business models. That means that the level 4 or 5 cars will be first introduced for commercial applications with restricted fields of application. One promising area are commercial delivery vehicles, because you can save costs in this case. For example, is hub-to-hub traffic, or later also last-mile traffic. So all the companies like UPS, Amazon, and so on work on automated robot cars delivering the stuff to the last mile as well. For the individual transportation, mobility as a service is a way for an affordable individual transportation. That means high utilization of the expensive cars and a low price for the individual to use it for transportation. To manage all this, the industry has to shape new alliances. First of all, to share technology. I think no supplier has all the technology at hand, and alliances are required to merge all the best. They also have to share the high development cost and investment, and they have to develop new service concepts. This reminds me to an older story like the portable music. So Apple, with the iPod success, did not invent portable music. It was available many years before with a cassette player. But what made the Apple model so successful? First of all, there was new technology with storage capability in a small form factor at a low price. And the second very important thing was the business model, always iTunes, that you can download music for an affordable price, which makes the customer experience a lot better compared to the past. And this is the step we have to go here also for the level 4 or 5 autonomous driving. As mentioned, autonomous driving requires a lot of innovation on the technology side. Specifically, the sensor performance and robustness. Luckily, radar has a huge potential for innovation still, and it can reach LiDAR-like resolution of today. I compare it always with the phone, and you can see there is a long history in innovation on the cell phones. And I would say today we are in the middle, maybe in the age of GSM, and there is still a long way ahead, innovation, new modulation schemes, and so on, and, until the smartphone and 5G like we know it today. LiDAR, as another very important sensor technology, is not yet meeting the cost and performance sweet spot. But also V2X as another external sensor is required. I'm personally convinced that autonomous driving will not work with massive V2X deployment, and therefore a lot of investment in infrastructure is required. Another challenge is the type approval of the cars. Road testing is done today, and this needs to be replaced to a large extent by improved methods like virtual integration using simulation, and vehicle-in-the-loop approaches means doing road tested in the lab under a controlled environment. The number of tests you have to do is exponentially increasing compared to today's cars, and road testing alone will not work anymore. But I'm also convinced, and this again a good comparison with the cell phones, standardization is required for mastering this system complexity. So a cell phone is a very complex system today as well, and it works robust. And the reason is why a lot of things are standardized, even the testing and all the type approval procedures. And I think this is also required in the automotive area. Radar remains a key sensor, and its innovation is a key enabler for autonomous driving. We are talking about 4D radar. It can reach LiDAR-like 3D image resolution in the range of 100,000 detectable reflections with a high number of virtual channels and large antenna apertures or even virtual aperture. And just to give you a little bit of an impression, on the right side of the picture, today's high-performance radars see something like the example you see on the left side. And just as a vision, the future radars could see much more, much better get much more information, and can do also object detection and get a much clearer picture of the environment. The big advantage of radar is also the Doppler and micro Doppler, which gives you a high resolution velocity information instantaneously for every reflection. That's why it's called 4D radar, fourth dimension velocity. A very interesting area is modulation. Today, FMCW is state of the art, but the FMCW is not very robust to interference, and this is a concern for level 4 and level 5. New schemes like PCMW, phase code modulation, or OFDM are currently under investigation, and they will enhance the robustness against interference. Antenna aperture is a very important topic for resolution, and virtual aperture is one of them. That means if you have two radars, for example, on the left and the right corner of the car, you can use the transmit signal of the left radar and receive it with the right radar if the radar are synchronized. And this gives you a very large aperture compared to today's radar, and can be done, for example, using phase code modulation so that you can synchronize on the signal of the other radar over the air even. Artificial intelligence is another area for innovation. This will improve object detection and tracking capabilities. Unfortunately, it cannot just be used like it's used in the camera, because the signature is different from a radar. So research is going on here, and a lot of progress is expected as well. What's going on in the frequency range? 60 gigahertz was already mentioned, but this will used mostly for interior radar, because it's a license-free band with very low power requirements. So I don't think that can be used outside of the car in a reasonable way. 24 gigahertz will basically go away because the remaining narrowband is not really useful. So most of the activities for exterior radar are in the 76 to 81 gigahertz area. Unfortunately, there is different regulation, for example, different power level for long range, the 1 gigahertz range, and for the short range. Therefore, there are activities in many countries, and for example, in ETSI, there is a proposal, FCC did it already, to merge the regulation for the 5 gigahertz bandwidth, which gives you more resolution. For the future, currently 134 to 141 gigahertz is under investigation for ultra short range surround view radar systems. So there is a first report on the usability of this frequency range expected end of the year, and we do not expect it to become regulated before 2026. What is the impact of all these trends on test and measurement? it's a lot about liability, and this means again quality insurance. As you heard, there is not a lot of regulation and laws and insurance in place. So the liability risks are with the OEM, and they increase with every new function and higher SAE level functions. The slow regulation and standardization is supporting, but it's pretty slow and does not help so far currently. That means the OEM is responsible and has to take the lead on radar quality assurance. And we can see that we work with many OEMs, and they ask us what can we do to improve the quality. And they do, for example, compliance monitoring during module production, meanwhile, which they did not request before. They do end-of-line testing of radomes, of bumpers, and radar mounting. And also a very new topic, they want to test radar functionality under EMC stress. So OEMs, even if this is not regulated, they develop procedures for testing and improving quality together with us and put it into their requirements for their supplier. A very hot and challenging topic is the homologation of new functions, which requires traffic scenario testing. I mentioned before, you need many tests for functions, and there needs to be a database shared between the suppliers and hosted by the authorities to get a type approval of a car. And finally, radar robustness against interference is a major concern, and action needs to be taken. I come back to that later. So how is Rohde and Schwarz helping to tackle all these challenges? First one is the microwave imaging used for radome bumper and radar mounting accuracy. It is used for radomes, for design emblem design, for bumpers, and also for paint and other cover material investigation. It is used during the development, in quality inspection, and also in end-of-line production. One important equipment is the QAR you see on the left side, which is pretty familiar with the airport security scanner, you might know. It's a super high performance radar system covering also the automotive radar frequency band. And for complex design emblems, for example, with many layers, homogeneity is very important, so that is controlled in production. For bumper, the quality of the molding, the thickness, if there are some intakes and so on, is very important. So transmission is monitored specifically. And for the investigation of new covers like paintings, epsilon R and S parameters are measured using a VNA, for example, a vector network analyzer. Another very new and exciting application is vehicle in the loop. Vehicle in the loop reproduces road testing in a lab in controlled and safe environment. We partner here with the company ABL. They are a huge testbed provider and provide all the control software to control the car and stimulate all the mechanical and also the ADAS sensors. So you introduce the road scenario coming from a test database I mentioned before, and then you stimulate all the objects, all the wheel, braking, steering commands like you drive it on a real road. And Rohde and Schwarz developed here a very new radar target simulator solution, which is extremely scalable with many independent objects, much more than systems provide today. There is no mechanical movement of antennas involved like you can see this as systems today. So it's robust and it works in a shaky environment, like a drive test pad where the car is operating. And it offers the precise and repeatable tests in a lab. So very important for future type approval. Future type approval will be a combination of road test, of course, of vehicle in loop tests like this, and simulation. Another example is testing the electromagnetic susceptibility of a radar in full vehicle over the air environment. So you see a car here in an EMC chamber and a radar target simulator in front of it, stimulating simple scenarios. And the car and the radar needs to operate without any distraction. RX 108 target simulator is proven to work in EMC environments, and we did already successful field tests with several OEMs in the world. Finally, I want to talk about interference. There is this EMICO project started in 2018 and still going on. This is funded by the German government, and that's the first project in the world where almost all big radar suppliers and OEMs work together to investigate interference, propose tests for interference, and also mitigation. So what was done in the project? The participants defined scenarios for interference, like parking lots, like highway traffic jam, intersection traffic, and so on. Scenarios where you have many radars, many cars meeting each other. Then they went on a huge test track with many cars equipped with all the radars from each supplier and reproduced all the tests on a real test track and measured the interference. As a next step, they reproduced the major effects measured on this test track using a radar target simulator from Rohde and Schwarz. And currently, they work on proposals for standardization to mitigate interference for FMCW. And this setup, our target simulator RX 100A, together with the signal generator, is used as a reference setup in this EMICO project. So in the ATS 1500 chamber from Rohde and Schwarz, the radar signals were recorded. Then they are manipulated with the pulse sequencer software according to the trajectory you want to test. And then the signal generator is replaying this generated sequence. The RX 100A is up-converting it to the RF frequency and adding it to the signal of the radar under test. So this is the end of my presentation. Thank you very much for your interest. If you have more questions, are interested in our solutions, please visit our website and the radar solutions for automotive radar. And you will find there also a poster showing you the trends and some solutions of radar. So that's and some parameters of future radars. So feel free to download or order this poster. Thank you very much. If you have questions, just feel free to ask. Thank you.
For the following session, we have the manager of INS. He's going to talk about new requirements for EMC specifications of automotive parts in the era of Internet of Vehicles. Good afternoon. It is the last section. It was quite hard for you to enjoy all these sections. We'll spend about 45 minutes to talk about the specification of automotive parts, and especially in the new requirements for EMC in this era. Our agenda today can be divided into several subtopics. We will discuss about why we do EMC tests for parts and for cars, and how do we run the automotive EMC testing. Also, in the new era of Internet of Vehicles, what's the trend in automotive EMC? What are the new requirements and new testing environments? Then we will talk about what can we offer. Not just single solutions such as receivers, we can also provide turnkey solutions. And then I've left some time for Q&A and for discussion with you. In the era of the Internet of Vehicles, when we just received our driving licenses and we drive, the cars, how comfortable they were, and the communication equipment in the car was very different from the cars nowadays. Now we have anti-choking systems, radar, GPS system, navigation system. 2 decades ago, we don't have all those equipments in the car. So with all these signals, while we could have a very safe and comfortable driving experience, but these signals could cause risks for us. And we want to know if there are risks. That is why we want to go through an EMC test, both for car parts and for cars. That is why we are going to talk about the EMC test and the new requirements for these tests. In the car, we have new devices, including infotainment systems. We have mobile applications and navigation system, and of course, safety systems. All these applications offered great convenience for us and also guaranteed safety for us. However, the signals of these systems during the communication of these systems, do they have disturbance and affect different devices and put in risks to how they function? That is why we have to put some requirements for the EMC testing to make sure that these devices can work normally. So for the regulations in automotive, here you can see an example. For example, European standards, we have a big E standard or small e regulation. The first one is compulsory, which is ECER 10. For these car use requirements, there are EMI and EMS, two standards. For EMI, is specific for RNF, which is including conducted and radiated tests. And the standards referring to those tests are CISPR 12 and CISPR 25. And for EMS, we have transient, we have RF, and conducted and radiated. The regulations for these tests take ECR 10 EMC, included CISPR 12 and CISPR 25, ISO 11451-4. And let's take a look on the new testing requirements for these standards. We can see that there are standards for emission tests. And the international standards include CISPR 25 and CISPR 12. For CISPR 25, it is focused on the parts for the cars, including limits and methods of measurement of radio disturbance, and how to comprise the method for the tests to meet the requirements for the regulation. As for CISPR 12, it is focused on the car. For the suitability standards, we have ISO standards as showed in the slide. And also in ISO 7637, it is focused on the component test method. I myself, apart from working for vehicle parts, I'm also specialized in in broadcasting, and which also included a vehicle. For example, DTB or radio test. We are also doing impact noise test. So the requirements for vehicles can be divided into two categories, EMI and EMS. For EMI, it is about CISPR 25 and CISPR 12. For EMS, the standards are ISO 11451, 452, and we have international standards. For example, CISPR 12, CISPR 12, and these requirements are also in line with major manufacturers. For example, GM, BMW, or Ford, or Fiat. In different countries, there are also different standards. For example, the European standards.
For CISPR 25 automotive component EMI, within it, there include conducted and radiated tests. For conducted test, we can do current EMI test as well as EMI voltage test. For radiated test, it includes a whole car test such as antenna test and onboard antenna test. So we can provide different tests in order to meet different requirements. For example, we can use team cell for testing. For those test requirements, we have to have a test receiver. Currently, in our company, our product is ranked as #1 because our test equipment, we call it EMI test receiver. Through it, we can receive signals. We can do image testing. I wonder if anyone of you has questions so far. Then we will move on. For the overall test, in addition to receiver, we have to have fixtures for both radiated and conducted tests. For the testing environment, it's set up in a chamber. According to the regulation, it has defined certain testing environment. So all the testing compiled with regulations. For immunity test, how to set up the DUT antenna so that we can do the immunity. Those are just for your reference. Next is the conducted immunity test setup. For ISO requirements, we can use a wide range of fixtures such as broadband antenna, thin cell, current injection, and etc. Those are for portable transmission test. For all our tests refer to regulation requirements. In the overview, for ISO 11452-2 to -10, it has the requirement of frequency domains, and it also has requirement for magnetic field. According to regulations, we have to follow for sure. Next, let's look at the current 6/25 updates. For 6/25 is defined by Committee D. For this current edition, it's a 4th edition. It's published in October 16. 6/25 contains national version. For example, EN 55025 is for UK and another for Germany. Its overall test refers to car makers' requirement. So each has different requirements. So it will vary to different car makers. Next, for edition 4, what's new? The most good news, I would say, edition 4 can use FFT-based receivers. For the EMI test receiver, we call it 10-domain slope. For 6/25, we can time domain scan. Therefore, it can refer to 6/16-1-1. With the proper use, of 6/8 ridge detector, the overall test frequency domain should be under 2.5 gigahertz. That is to say, for hybrid and EVs, there are some updates as well. Under 6/25, when doing vehicle test, there include antenna test while the engine is off. Such setting is referred to 6/12. And next is to improve accuracy. We have to enhance and include correction factor during the test. Before testing, chamber validation should be done. There are two ways. One is non-well, another is reference site method. Our EMC software can do these two methods. As we have included a high voltage test, it has to be under 50 volts for discharging. And from high voltage to low voltage, we have to include other parameters. It's worth mentioning that when doing the average detecting, we have a dwell time. This requirement seems not that appropriate because it's not long enough. According to average detector, when testing, there will include AM and FM and TV band, and etc. They all have their different frequency domains. When it's under 30 megahertz, we need to use 116 milliseconds. Therefore, we will say the dwell time is not that appropriate. When it's bigger than 30 megahertz, then we have to use 100 millimeters or longer. If the time is too less, then the result would not be accurate. So if today we have a wrong measure method, and if we use the FFT method, we call it time domain scan, then our period time is about 12 millimeter seconds. And then we can see a very clear and complete signals. With the time domain scan, and we use only 10 milliseconds, we will see incomplete picture of our emission signals. Maybe only half of them are detected. Those are so-called testing errors. Even we use step scan, we can see the signals come with the gaps. In conclusion, if today our measurement time is bigger than period time, that's what we needed.
Then let's take a look at what's coming in edition 5. When we talked about edition 4, the testing frequency and its maximal power is only 2.5 G. But since we have 4G, Wi-Fi, or C2X signals, or these GNSS signals, that is why in edition 5 we have a new requirement for 6 gigahertz. So from edition 4 to edition 5, we're going from 2.5 gigahertz to 6 gigahertz. Apart from that, we are trying to include other uncertainties. For example, when I talked about the known signals and its testing requirements, which is CISPR 12, CISPR 25, and ISO standards. Those are compulsory tests. And in the next field is the EME testing, which is electromagnetic environment testing. Why are we talking about this? Because for electromagnetic environment means that we're all in a EME environment. For example, Bluetooth earpieces that we're using every day. We don't use these pieces to listen to music, but to use it as a hands-free device for the mobile phone. We are under the exposure of many signals. For example, Bluetooth signals or unknown signals. And when these signals mix together, we have an intermodulation, which could lead to some unknown situations. For example, frequency 1 to frequency 2, there may lead to another frequency. And this situation would affect your devices in your cars. It is not a compulsory test in Taiwan, but we are hoping that some authorities would implement these tests. And in the working group of automotive, we are seeing advancements every day. For example, we're seeing ADAS, C2X, etc. These are all fields for studies for us. For example, for EME, we are including different communication signals in these testings. For a car in motion, these signals might affect the functions of these devices. And in the following slides, we can take a look of EMC and its differences with EME. So we have an EME environment inside the car and outside of the car also. So because we have cell phone communication, Wi-Fi or Bluetooth, etc., radio signals are also included in the inside vehicle part. Outside of the vehicle, we have GPS or other kind of signals too. So what's the effect of EME? It is the radio coexistence, which evaluates performance and functionality in the presence of non-radio and wireless communication signals. And in different environments, what would be the effects for our car or the devices in car? If you work in the EMC field, you might know that it is more related to the conventional EMS. For example, the non-signals, we could use pulse modulation or amplitude modulation. And as I've mentioned before, in EME, in an electromagnetic environment, it is an in-field environment, meaning that in this field, there are a mixture of different signals with different frequencies. These signals might create other intermodulation signals. So we want to duplicate these signals for testing. And how do we achieve that? The idea of this testing is from military standard. In the military standards, the concept already existed. They wanted to simulate signals to disturb other parties. For example, for military testing, they want to receive the signals and disturb that signals. But for the automotive EME signals, the difference between EMS and EMC, it is 80% of AM sweep. But for EME, it is about radar pulse wideband signals. So we are doing reliability, adaptability, and safety tests. In this environment, we want to see if the device can work normally. These are the EMC standards, including commercial standards, military standards, for your references. Right now, the EME tests are compulsory in the States and in China. In China, the standard is called the GB. Then, how do we run the EME test? We have to record EME signals. For example, today, I can make a detour in Taipei City and record the EME environment and bring it to the lab to play it. I can play it several times and duplicate it without any losses because it is a recorded signals. And within this environment, we can run different tests. So we have to have a software and equipment like IQW to record the signals. So in the EME collection and recording, we could use spectrum to see what signals do we have. Some signals would overlap each other or use the same channel. We could use this spectrum to analyze it.
When we bring EME signals back to chamber, including like GPS, telecom, failure signals, like Wi-Fi broadcasting car radar. Those signals communications can be recorded and be replayed in chamber. For example, I can drive around to create a scenario and replay it back in the chamber. For our solution, we can go to field for recording purpose. Then we store the data in IQW, and we can replace such data. So that's how we can do from field to lab. That's our structure. Finally, for our solution, we do from field to lab. In the future, different governments might set up different kinds of testing requirements. Like Wendy, she has been promoting the standards. So let's take a look on this. For automotive, we also cover other areas like medical, like wireless LAN, military, etc. And earlier, we went through standards, to test known and unknown signals. And we went down to EME. So now we move on to receiver. Our test receiver is the most complete and the most complex option. It's a great platform. So it goes from 1 Hertz to 44 gigahertz. Today we don't have a demonstration. However, you can look at the pictures here. Our unique functions include 1 dB compression point, great TOI. We have great displayed average noise level. If today you have test receiver and you can do automotive EMI or EMC tests, you also can do the test on car radars. From 44 gigahertz up to 70 gigahertz. That's for car radars. And lots of tests can be conducted. For EMI test, we can do scan, we can do peak search, final management, and etc. I have to emphasize that our real-time spectrum, time domain stem, they have different points. We do the traditional spectrum scan. For CISPR regulations, you can do the FT-based evaluation. That's based on time domain test. The good of it is it has good accuracy. It also can obtain fast measurement. For traditional way, so-called classical scan, it goes slowly and gradually. But for FFT-based measurement, it's go within FFT width. So it's more like a parallel idea. All the signals can be obtained at once. That is to say, for measurement times, for automotive testing, CISPR 11 includes automotive, including fast and dynamic 3 modes. So we can do flow comply from different time frames. So it can set up to 24 seconds. When comparing with the traditional step scan measurement, say today, I want to do CD bend or do a B bend. For traditional way, our step size is about 4K, and the time domain is 2.25 kHz. So with the traditional method, step scan, our measurement time is about 3.8 hours. With FAT-based time domain scan, it takes only 2 seconds. You can see there's a huge difference. So if you are from a lab today, I could say with the faster method can obtain the test result. It's worth mentioning, traditional way, the spectrum we get from traditional way have different from the time domain scan. But there's another one called real-time spectrum. It can do hopping signals. With the hopping signals, if we apply traditional method, it perhaps cannot keep up with the speed. With the real-time spectrum, its idea is to acquire signals and then process the signals. So it captures and analyzes. However, we have some blind time. So with the real-time spectrum, it's mainly applied for military fields in order to solve pulse problems. So if real-time spectrum is good enough, we can capture pulse signals. Those here, we have different signals in signals. This cannot be obtained by other methods. Finally, I have to promote our product, our test EME system. It's our solution with our powerful FSW and IQW and IQ recorder. It can record a very long time because the hard disk can be replaced. Therefore, we want to give you a brand new idea, a brand new concept. So when we work with NCC, we do a lot of testing. We just recall the environment and we replay back in the chamber. And our solution is for EME particularly. Some other suppliers may apply similar idea, but not for EME solution. As far as I know, in Brazil, and in the States, they recall the local fields. It also applies similar solution as I described. However, our product can go as large as 512 megahertz. As a final section, I would like to thank you for staying to the last. I would like to know if any one of you have questions. If no, then I will give the floor back to our beautiful lady, Wendy. Thank you all for staying to the last minute. In closing, I would like to give the floor to Rebecca, who is the organizer of today's event. I would like to remind all of you to fill up our questionnaire. We have online and offline platform today, so we would like to hear from you. Let's welcome Rebecca.
We have QR codes in your seats, or you can scan the QR code in the screen. There's a questionnaire. It will take you only 3 minutes to take these questionnaires. And while you are filling out the questionnaire,